Welcome back, young students of AP Chemistry. This is a short recording regarding the gas laws. Now, in honors chemistry, we didn't actually call the gas laws the gas laws. We just looked at relationships between pressure and volume, pressure and temperature, and pressure and the amount. And we were like, oh, well, I know that if temperature goes up, that means that volume is going to go up, and then we just made that happen by multiplying it by a fraction. I do want to give you the names of the laws this year, because sometimes I think you're expected to know that. I don't think they're of value, but I think you're expected to know that. So first of all, please remember that pressure is a property that is caused by collisions, right? So pressure is caused when particles collide with the side of their container. So it makes sense that the smaller the container, the more often those particles are going to collide with the container. And it makes sense that if the particles are moving faster, meaning they're at a greater temperature, they're going to collide more frequently with the container. We measure pressure in the classroom using a barometer. I don't think I have a picture of that up there. But in chemistry, if we have a gas that is we're not measuring atmospheric pressure. We measure those with a manometer. So a barometer for measuring atmospheric pressure, a manometer for measuring a gas by itself. Now, in a closed-end manometer like this one, what we would have in here is, well, this is a lie, but what we would have in here is mercury. We don't use mercury because, well, mercury is dangerous. But in a closed-end manometer, this area above the mercury up here is a vacuum. I'm not going to try to spell that. I know there's two C's and two U's. Two U's, one C. V-A-C-U-U-M. No E. Vacuum. So when we are measuring a gas pressure in a closed-ended manometer, this change in height is equal to the pressure of the gas. And that would be if there's mercury in that manometer, that would be measured in millimeters of mercury. The height in millimeters of what it's pushing, mercury. Now, when you do your lab, you're going to have water in there because mercury is dangerous. So you're going to measure that in millimeters of water, and then you're going to convert it. What do you have, Patrick? Yes. We would write it as millimeters of whatever is in there. Water, silicone. It has to be a liquid, and it has to be a pretty heavy liquid. Otherwise, the height gets so high that the tube on the manometer would have to, like, I don't know, be 3 or 4 stories tall because the gas would just push it that high. So we have to have something relatively dense in here and something that's a liquid and something that's not reactive. So sometimes silicon compounds are put in there. There's this compound called liquid glass, and it's like silicon dioxide. They often will use that in a manometer as well. It's not very clean, but it works. Okay, in an open-ended manometer, we are comparing the pressure of the gas to the pressure of the atmosphere, because what we have here is the atmosphere pushing down on the gas. So this is a comparison, and again, we would look at the change in height, and that would be expressed in millimeters of whatever the substance that is in the manometer is. And the comparison then depends on whether the pressure of the gas is greater than or less than the pressure of the atmosphere. So at this point, you just have to look at it and see, well, which one is pushing harder. Is the gas pushing on the liquid harder, or is the atmosphere? And the way I've drawn it here, what's happening? Gas is pushing harder. So the pressure of the gas is greater than the pressure of the atmosphere. Then to calculate that pressure, you would do pressure of the gas is equal to pressure of the atmosphere plus the change in height. And just make sure that those two pressures, the change in height pressure and the atmospheric pressure, are in the same unit. In an open-ended manometer where the pressure of the gas is less than the pressure of the atmosphere, it would look like this. Oh, wrong. It would look like this. Still measure the change in height, but then we would do the pressure of the gas equals pressure of the atmosphere minus the change in height. So if you have to convert from one unit of pressure into something reasonable, like millimeters of mercury, those changes in height are dependent on density. So we can use just a simple ratio and say that the density of, let's just pretend there's water in the manometer. The density of mercury, or the density of water, is to the height. Wait a minute, something doesn't feel right. Density and delta H are inversely proportional. So, density of water is to the change in height of water as the density of mercury is to the change in height of mercury. Change in height of mercury. That says delta H sub Hg, mercury. Do you guys understand why I have density of water on top and the change in height of the water on the bottom? The more dense it is, the smaller the change in height it's going to be, right? If it's more dense, it's going to take more pressure to push that liquid, which is why they're flipped. So you could use that to solve for the change in height according to mercury, which then is a valid unit of pressure. And you will have to do that in your gas stoichiometry lab. Okay, common units of pressure. Atmospheres, my favorite. 1 atmosphere is considered standard pressure. I think that just makes sense. We abbreviate atmosphere ATM. If we're looking at standard pressures, another unit of pressure and standard pressure would be kilopascals. And kilopascal is actually the SI unit of pressure. 101.325 kilopascals. And 101.3 kilopascals is equal to 1 atmosphere. These are all standards. Do you guys remember what it is in millimeters of mercury? What? 727. No, close. It's in the 700s. Close. 760. (760) millimeters of mercury. And you understand the unit, millimeters, symbol for mercury, Hg. And then the other one is torr. That is not a very common unit of pressure. It's really torque, right? The rotational pressure on like a nut or a bolt. But it's the same thing as a millimeter of mercury. These are all equal to each other, yes. I feel like a call center person. Okay, so the ideal gas law, we are fond of calling it PERVNERT, PV equals nRT. It's really called the ideal gas law. That's derived from kinetic molecular theory, and we're going to talk more about kinetic molecular theory later. But that shows us the relationship between pressure and volume, amount, temperature, and whatnot. So pressure and moles are directly proportional if everything else is held constant. So if we put pressure in moles, right, N is equal to, or P is equal to nRT over V. If R is the universal gas constant, but if temperature and volume are held constant, then pressure is directly proportional to moles. So oftentimes, if you have a mixture of gases, and you know, oh, the pressure of the mixture is 8 atmospheres, and you know the mole ratio or the mole fraction, then you know the pressure of each individual gas. That's called a partial pressure, the pressure of each individual gas. So pressure and amount directly proportional. I think that's all I was going for there. What does your paper look like? Oh, so it's a combination of Boyle's law, Charles's law, and Gay-Lussac's law. His name really is Gay. It's oh, I skipped a slide. That's why we're on the back. Well, let's go back. Here we go. This is where you should be, right? So standard pressure, we talked about that. 1 atmosphere, 760 millimeters of mercury, 101.325 kilopascals. So in honors chemistry, you learned that Boyle's law, you learned the relationship between pressure and volume. So as pressure increased, or as volume increased, what happens to pressure? So increased volume, pressure decreases, right? Which makes sense. There's going to be fewer collisions per second with the wall of the container. So this is what you learned. This, by name, is called Boyle's law. You did a lab where you measured pressure and volume, and you got this in a graph. So you can either just make that happen, or Boyle's law equation says that volume 1 times pressure 1 equals volume 2 times pressure 2. So you can work through it algebraically, or you can work through it logically. It doesn't matter to me. Yes?
So is it volume and pressure are directly proportional?
Inversely proportional. Oh, I drew the wrong graph. Sorry. Yeah, it looked like this. Thank you, Jacinta. It's the old lady brain. Why do you have to get old? I do not like getting old at all.
You're like 19.
What?
Like 19. You're basically our age.
Oh, Patrick. As if I could love you more. That's really sweet, but I know it's a lie. It's a lie. So the graph looked like this, and it wasn't exponential. It wasn't exponential decay of the pressure, because the pressure can never go to 0 if there's any substance present. So it's asymptotic. Is that a word? Forms an asymptote? Asymptotic?
Sure, go for it.
I like the word asymptotic if it's real or not. What? Oh yeah, it's awesome. I make a, if there's substance present, the pressure can never go to 0. Yeah. Okay. In honors chemistry, we also looked at the relationship between volume and temperature. So an increase in temperature led to what? Do you remember? Increase in pressure. And what about the volume, though? Now, if we're looking at the relationship between volume and temperature, if temperature increased, so think about a balloon, something that's volume can change, right? If we have a balloon with a certain amount of gas in it, and we increase the temperature, That's going to increase the pressure. What's going to happen to the sides of the balloon? As the particles hit the sides of the balloon's going to do what? It's going to stretch. It's going to expand. So the relationship between temperature and volume is that as temperature increases, volume increases as well. So this is a direct relationship. You know what? I guess we didn't study this one last year. You didn't do this in your lab. Yeah. So if you had a graph of volume versus temperature, it would look like this. Should it go through 0, 0 at temperature 0? What should the volume be? At Kelvin temperature 0? Yeah. The theoretical absolute 0, if there is 0 temperature in Kelvin, there'd be no movement. So the volume would theoretically be 0.
Wouldn't the pressure be theoretically 0.2?
You need to go away. The equation for Charles's law, V1 over T1 equals V2 over T2. Remember that when we have fractions and an equals, we cross multiply and divide. And that temperature must be expressed in kelvins. Do you guys remember how to get Celsius into kelvins? Kelvins equals what? Celsius plus 273. Let's put some point zeros on there, because most of our thermometers measure to the tenths place. Avogadro's law was the relationship between volume and amount, and it makes sense that the more gas you have, the what volume? The greater the volume, right? More gas, greater volume. So you increase the moles, increase the volume. We looked at that relationship with pressure. And that equation would be, that's also a direct relationship, so that equation would be N1 V1 equals N2 V2. So I guess the thing that's important to remember when you consider the ideal gas law is that for this to be true, the temperature and the pressure must be constant. If the temperature and pressure is changing, that is not an accurate statement that those are directly related. So if we go back then to Charles's law, what has to be held constant here? Constant what? Pressure and amount. Good. And then for Boyle's law, what's held constant here? Temperature, thank you. An amount. I knew you said something, I just didn't hear what you said. Didn't we already put something there? That's weird, it went away. Avogadro's law. I have it twice? Whatever. Gay-Lussac's law. He's French. Oh, it's not on your paper? All right, we don't have to do it. It's inherent. So here's the thing that we might want to put on there that's not on there, is the combined gas law. Is that on your paper? The combined gas law combines Charles Boyle's and Gay-Lussac's law. No, that's ideal gas law. Just shove in the combined gas law somewhere. And it says, so it combines Charles Boyle's law, Charles's law. This is Gay-Lussac's law, the pressure-temperature relationship. So in the combined gas law, what's the only thing that's held constant? Amount of the gas is held constant alone. So if you did Gay-Lussac's law, that'd be P2, P1, T1, P2, T2. So as temperature increases, pressure increases. The combined gas law combines Boyle's, Charles, and Gay-Lussac's law.
So what's the ideal?
The ideal gas law?
I thought that's what.
PV equals nRT.
I thought that's what combined Gay-Lus Charles.
Boyle, Charles.
They have made more than one.
Wait.
More than one gas law.
Wait,
So listen, all of the gas laws are derived in some way from the ideal gas law. Okay? The ideal gas law takes into consideration moles, whereas the combined gas law does not. So you're assuming you have a constant amount of moles of gas. And the ideal gas law is when you don't have repeating conditions. So like the ideal gas law is just, okay, what's the pressure if we have this much at this temperature, and so on, right? Whereas the other gas laws are you have a set amount. If we change the volume or the temperature, how does that change the gas? Okay, now on to
We need the constant.
the ideal gas law. So the ideal gas law combines, you know what? That's supposed to say, so the ideal gas law combines all three of those except Gay-Lussac's, Boyle's, Charles, and Avogadro's law. So the ideal gas law combines Boyle's, Charles, and Avogadro's law. The combined gas law is Boyle's, Charles, and Gay-Lussac's law. Okay, so the equation for the ideal gas law, PV equals nRT. The universal gas constant, R, universal gas constant, that's 0.0821 atmospheres times liters over moles times kelvins. So the important thing to remember when you're using the ideal gas law is that the unit for pressure must be in atmospheres. Lie. The unit for volume must be in liters, and the temperature must be in kelvins. But that's the temperature being in Kelvin is for all gas laws. Okay? Now, what? No, it's just a dash. Not negative. It was just a bullet statement. Poorly made. It was a poorly made bullet statement. So, density in the ideal gas law, where was that? My slides are out of order. Here we go. Of course, density in the ideal gas law combines the ideal gas law and it's sort of molarity, moles per liter. I'll just take really quick derive it for you. So if you have the ideal gas law, oops, PV equals nRT, right? If you solve this for density, sort of, that would be N over V. The amount per unit volume would be density. We don't typically use moles. We typically use grams. But if we solve that for N over V, that's equal to P over RT. Is that right? Yeah. And if we know that if we want grams per, so moles is molar mass is grams divided by molar mass. So grams divided by molar mass over V equals P over RT. You with me there? To get moles, we do the mass divided by the molar mass. So if we solve this for molar mass, so we're dividing, which means we multiply by the reciprocal. So P over RT times V over 1 equals molar mass. You with me there? So I'm solving for molar mass. right? So I'm dividing the molar mass, I'm dividing this fraction by this fraction. So I want to get rid of it, so I'm going to multiply by the reciprocal, and I have to do that to both sides. So molar mass is equal to PV over, no, did I do that right? I don't want to put in molar mass yet. So grams per mole equals PV over RT. No, something's not right.
Grams per molar.
Oh yeah, that's right. I'm sorry. Right, okay. It's not grams per mole, it's grams per molar mass. So grams over molar mass equals PV over RT. So if we solve for molar mass is equal to GRT over VP. You with me? I just cross multiplied and divide. G times RT over PV, and then I solve for molar mass. So then G over V is equal to what? Grams per volume is what? Density. So molar mass is equal to DRT over P. That's what you want. Molar mass is equal to DRT over P. I always remember it dirt over Peter, because Peter stood me up on a date one time. Therefore he should die. Yeah, Peter was a jerk. He just looked really pretty. Yeah. Should have gone for the brain. He was clearly stupid. Huh? Yeah. It's for Laura and yeah, Grace. All right. So Dalton's law of partial pressure, a mixture of gases at the same temperature. So Dalton's law of partial pressure says this: if you have a mixture of gases and the temperature is not changing for the gases, they're all at the same temperature, the sum of the partial pressures of each gas is the total pressure of the mixture. Sum equals total. You guys, this is not, rocket science here, that the sum equals the total. So if you think about an equation form, that's going to be the pressure total is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. Oop. Plus the pressure of gas 4 plus the pressure of gas 5 on to infinity, right? Onto however many gases are possibly present. And this is where we can use a mole ratio to distinguish partial pressures. Each one of those pressures of the gas mixture is called the partial pressure. So if you consider atmospheric pressure, right? What is mostly in the atmosphere? Right, so in the atmosphere, we have mostly the pressure of nitrogen plus the pressure of what's next? Oxygen. What's the next most common gas in our atmosphere? Carbon is not a gas. Carbon is a black solid. Nitrogen, oxygen. Carbon dioxide probably is the next one. And then we have trace other gases. We have a little bit of neon, a little bit of radon, a little bit of argon, a bunch of other junk mixed in there. But they're in really small amounts. I'd have to look that up to see if carbon dioxide is the third most abundant. I don't remember. Okay, so I have two example problems here. Let me look at them and figure out exactly what I wanted to do with them. I cannot be sure. So it says we have on the first problem, half a mole of hydrogen at 20 degrees Celsius is mixed with 1.25 moles of helium at 20 degrees Celsius. And I'm assuming by it saying it equals um, I don't, the box is the same size, so I would say that the volume is constant. I don't know. So what we're doing is, I should have made myself some notes on that picture because I'm not exactly sure what I'm wanting to represent or even what we're solving for. So let's pretend. So we're going to pretend that we're mixing 1.25 moles and half a mole. Temperature's changing, volume temperature is not changing, and the volume is not changing either. So I think what we want is, hey, what's the pressure? Right? So here we're going to solve for pressure. We're going to assume that this volume is the same as the volumes originally in the boxes. Right? So our final volume is not any greater than what we would have started with each gas. So here we can solve for the pressure of this gas. Pressure is nRT divided by P. Oh, it says 5 liters. Does yours say 5 liters?
No.
Oh, well, that's important. So here's a couple of ways we can solve this problem. We can solve for the final partial pressures at a volume of 5 liters, and I'm saying that because it started out 5 liters, and this box is the same size, so it's probably still 5 liters. So we can say, okay, if we want to know what is the pressure of the hydrogen gas, right, then we can say temperature and volume are held constant, right? So the amount is 5 moles. No, we shouldn't do that. So if we want to solve for the partial pressure here, nRT divided by P, no, PV divided by V, right? 0.5 times 0.0821 times 298, 70, 80, 90, 293, 0.5 times 0.0821 times 293 over 5. So the pressure of the hydrogen gas, you're going to have to chug that out really quick. I'm sorry, what? 2.4 atmospheres. That's a lot of pressure. That's the partial pressure of the hydrogen. Do the same thing for the helium. .25. Oh. 0.0821, 293 over 5. So the pressure of the helium is what? 6.0 atmospheres. So the pressure of the mixture is 6 plus 2.4, 8.4 atmospheres. So another way you could solve this problem, which I actually like a little bit better than what I just did because it's less work, I would solve for the final pressure. Pressure final, or total, is equal to the total moles times R times the temperature over the volume, right? And if you solve for that pressure total, your moles total would just be 1.75 moles times R times 293 over 5 liters. You should not get the same answer, shouldn't you? 8.4? Is that right? So if you did that, just know that you have to total your moles. Now, if you wanted to know the partial pressure of each gas, that's where you could use your mole fraction and say, okay, if I want to know what is the partial pressure of hydrogen, I'm going to take the pressure total and multiply it by the mole fraction of hydrogen. So that's going to be 8.4 times the mole fraction of hydrogen, which is 0.5 divided by 1.75. That's moles of hydrogen over moles total. And that should give you this 2.4. So there's a couple ways you can go about this. I think I like this way better. To get the total pressure, and then if you want the partial pressures of the gas, you can just use a mole fraction. Isn't this picture cool? I drew this on Microsoft Word. I went into this thing, all of a sudden I wanted to start drawing a bunch of stuff on Microsoft Word. Do you see what it is? It's a stopcock. You turn it and open it up.
It looks really nice.
Thank you. That's what I wanted to hear.
Good job.
That's a really great drawing. And notice that we have a 2-liter container and a half-a-liter container. Okay, so probably that is not to scale. I didn't do that very well. This is clearly not that much smaller. So if we want to do the, what is the total pressure once we open the valve? So we're going to assume that this portion of the apparatus has a volume of 0. So the new pressure, the new volume once we open the valve is a total volume of 2.5 liters. So if we want the total pressure, we need the partial pressure of each gas. If we want the pressure of the neon gas, the pressure of the neon, we can use the pressure now to calculate what is the pressure at a different volume. The temperature is held constant, so we can ignore the temperature. So the pressure of the neon, pressure 1, at the volume of 2 liters is equal to pressure 2 at the volume of 2.5 liters, right? So if we want to know the pressure of the neon at 2.5 liters, we can just solve Boyle's law here. Pressure 2 is equal to the pressure 1, 420 torr, at the original volume of 2 liters, divided by the new volume, which is 2.5 liters. You guys, should the partial pressure of the neon go up or down? What's happening to the volume? Volume's increasing. What's going to happen to the pressure of the neon? It's going to decrease. So last year what we would have done is just made a fraction out of the new volumes, 2 over 2.5, and multiplied it by the 420. We're doing the same thing mathematically by using the algebra. We're saying, hey, this number needs to get smaller, so we're going to put the 2 liters on top and the 2.5 liters on the bottom. So the pressure of the neon $840 divided by 250, 2.5. 84 divided by 25. Can't do it. What is it? 13? 336? Torr. Do the same thing for your helium. Pressure of the helium is equal to the original pressure of the helium, 1.5 atmospheres, times the change in volume of the helium, 0.5 liters to 2.5 liters. I can do that. 1.5 times 1/2. 1.5 times 1/2. Half of 1/2 is 0.75. Divided by 0.25 is 3, so it's 0.3 liters, 0.3 atmospheres. Now, we can add these together. Can we add them together right now? No, we have to change that unit. So pressure total is equal to 336 torr, which we're going to convert into atmospheres by dividing by 760, because it's 760 torr per atmosphere, plus 0.3 atmospheres. You didn't have to go to atmospheres, but that's my favorite unit of pressure, so I always go to atmospheres. That's the gas laws. Save.